Hi and welcome to the first part of this video series about the Kerberos deep dive. My name is Alex and I work as a security analyst for a company in Switzerland called Compass Security. My daily business revolves around ethical hacking, penetration testing, red and purple teaming. And during the engagements with our clients, we regularly encounter the Kerberos protocol, specifically when we are performing penetration tests of Active Directory infrastructures. And from these engagements, we have built up quite an extensive know-how about Kerberos, which we would like to make available to you with this video series. Now, who is the series intended for? We are going to talk about different aspects of Kerberos. First, we'll learn how Kerberos works under the hood, and then we also cover certain attack techniques, and lastly, we also talk about how you can defend yourself against those attacks. So no matter whether you are a pen tester, work in other fields of security, or you are a system engineer, responsible for the Windows infrastructure at your company, this series might be of interest to you. Now, before we jump into the content of the first part of this series, let's quickly talk about what topics we are going to cover. In the first part, we start with an introduction to Kerberos itself, so how the protocol works under the hood. In part 2 and 3, we'll look at different attack techniques called Kerberosing and AS-REQ roasting. And in part 4 through 6, we talk about the various delegation features in Kerberos, how they work, how they can be abused, and how you can secure them accordingly. So without further ado, let's start with the Kerberos introduction. So what exactly is Kerberos? The Kerberos protocol in its initial form was developed by the MIT in 1988. Now, this is not the exact version that we are going to talk about in this video series, since we will be looking at the Microsoft version of Kerberos, but more details on this later. Kerberos is named after the three-headed dog Cerberus that guards the gates to the underworld in the Greek mythology, and its main purpose is to serve as an authentication protocol in potentially untrusted networks. So the way it has been designed is that it allows secure authentication in a network or in an infrastructure where you might have potential adversaries eavesdropping on your communication. The authentication is performed by a trusted third party, the so-called KDC or Key Distribution Center. Again, more details on this later. And what Kerberos allows is that the involved parties can prove their identities to one another. So they can achieve mutual authentication and from that on then establish secure communication channels. The whole system in Kerberos is based on so-called tickets that are issued to the individual participants and then exchanged between them. And these tickets carry identity information that is cryptographically protected. Now, the whole cryptographic principles that are used rely solely on symmetric cryptography, so we don't have any public key infrastructure or similar things involved in Kerberos, and this then also explains why we need to rely on a trusted third party that acts as a central point to facilitate the communication and also the key exchange between all other involved parties. So, as already mentioned, the goal of Kerberos is to achieve authentication, specifically mutual authentication, and establish secure communication channels over an insecure or potentially insecure network. So within that network, we might have different participants like users and servers that offer different services like database, web applications, file share, and so on. And within this network, or for the participants in a Kerberos realm, there already have to be some secrets pre-established. This is achieved by integrating Kerberos into the Active Directory environment and taking advantage of the fact that every account or every user in every system in an Active Directory already has a password assigned, and Kerberos then simply derives, or for Kerberos, the secrets, the initial secrets for each participant are derived from the account password that this user or machine already has. This is then called the long-term secret or long-term keys, which are used for authentication purposes. And what we want to achieve, as mentioned before, is to be able to establish secure communication channels between the individual parties. So maybe the user up here would like to communicate with the database, later on the file share, and then the web application. Same for the other users. And for each of these channels, we would like to establish a secure or we would like to establish a secure channel, and for this Kerberos can be used to exchange so-called session keys. Now, these are temporary in nature, so in contrast to the long-term secrets that are already pre-established, and those session keys are then used to secure the actual communication channel between the two participants and dropped afterwards. Now, in this video series, we'll be looking at a specific version of Kerberos, namely the Kerberos version implemented in Windows. Microsoft has their own implementation of this protocol called MS-Kyle. You can find the standard or the documentation referenced in the link below. And this version has been extended by Microsoft, has some additional features compared to the original Kerberos, and has been around since Windows 2000. It is the default authentication package or authentication mechanism in Windows, so whenever you access a service within an Active Directory environment, there's a high chance you'll be using Kerberos in the background. It was initially intended, or it's still intended, to replace NTLM as an authentication protocol. However, as you might know yourself, NTLM is still widely used and is actually quite hard to get rid of. The main goal of Kerberos in Windows is to enable users to access resources with their Active Directory credentials, so not have a different set of credentials for every service, so essentially single sign-on. Now, what is specific in a Windows environment, so Kerberos works, is that every service that you want to access with Kerberos has to have a so-called service principal name, or SPN for short, registered within the domain. We'll look into more details about this later. Another detail is that Kerberos essentially only works whenever you access a service over its fully qualified domain name or the net bias name, not with the IP address. There are some ways where you could make it work with IP addresses and register the IP in the service principal name. However, this is rarely done since IP addresses are often prone to change quite frequently. Now let's look at the main building blocks that are used to create a Kerberos or functioning Kerberos environment. The main context where we are in is called the Kerberos realm. It groups together all clients and services that use a central instance of the KDC to authenticate to one another. So within this realm, we might have users or clients. We have services that offer some like a database, file share, or application. And all these services, as mentioned before, must have a service principal name registered within the domain. And then essentially in the middle, to mediate between all the different parties, we have the key distribution center. Now, the key distribution center is split up into two logical parts. On one side, we have the so-called authentication server, and on the other side, we have the ticket granting server. We'll see later what their purposes is exactly. And as we've learned before, there are different keys involved. We have namely the secret or long-term secrets keys, and we have session keys that are used to secure individual communication sessions. And then eventually we also have tickets, mainly two types of tickets, a so-called ticket granting ticket and a service ticket. And we'll look at more details about these tickets later on. First, a bit more information on the KDC. The KDC is, as mentioned, this trusted third party in the middle that mediates between all the other parties. And this is implicitly configured or installed on the domain controls within your domain. So this is not a server role you have to configure on a specific server. Now the KDC, as it lives on the domain controllers, has also access to all the key material, the Kerberos key material, which is stored on the domain controllers of all users or all accounts in your domain. As we've seen on the previous slide, it consists of two logical services: the authentication server, which is responsible for authenticating clients that connect to it and issuing so-called ticket granting tickets, and then the ticket granting server, which accepts clients that have already been authenticated by the authentication server and issues so-called service tickets that then are used to access specific services in turn. A bit more information on service principal names. A service principal name, or SPN for short, is basically a unique identifier of a given service instance, of a unique service instance within your domain. The format is always structured the same way. We have the so-called service class, which indicates the type of service you're talking to. That could be www for a web server, that could be LDAP or MS SQL service, and so on, for the different categories of services that are available in the domain. Then we have, as a second part, the host that actually is exposing the service. Again, here you would either use the fully qualified domain name or the NetBIOS name, ideally both, where this service can be reached on a system in your domain. The last two parts, the port and the service name, are both optional and only used for specific cases. An example of how an SPN might look like is shown below. So we have an instance of MS SQL SVC, so a MS SQL database running on the host ws1.winattacklab.local on port 1443. Now when you configure this SPN, you actually map it to an account that is then running this service in the background. And Kerberos then uses this SPN to associate the service instance that is running by this indicated by this SPN with the specific account you specified during the SPN definition. And with that, Kerberos is then able to retrieve the correct key material when you want to talk to the service. Now it's interesting to know that in Windows or in a Windows domain, some of the SPNs or a lot of the SPNs are created automatically when you create a domain or when you create a new machine and join it to the domain, while others have to be added manually whenever they are required. Now let's look at a real-life example, how SPNs might look like in a domain. I'm in our test environment here. We're going to use that throughout the whole video series, and I'm on the domain controller and have a PowerShell instance open currently. There are different commands available to inspect SPNs. We are going to use the set SPN tool for now to list all the SPNs configured in our domain. In the output, we can see for every account that exists in our domain that has at least one SPN associated, all the SPNs that have been configured, either implicitly or explicitly. So, for example, for the domain controller, we have a whole list of service principal names, and you can see that they are specified using different naming conventions, formats, so with only the NetBIOS name or also the fully qualified domain name, so you can reach the service via both notations, for example. The same thing is true for the client as well. We have some SPNs configured there in the same manner. Now, most of these SPNs have been configured automatically, so a domain admin didn't have to do anything. In comparison to that, we have also two SPNs highlighted here that are configured explicitly. So one HTTP SPN that is associated with the IIS service account, and one MS SQL service SPN, which is associated with the SQL service account, so to operate the database and the web server respectively. Now, one of the SPNs that we see here is a bit special in its own right. This is the host SPN, and the speciality about this host SPN is that it is actually a mapping for various other SPNs that are then also available on the given system. So if we have, for example, host on DC1, that means there are actually a lot more SPNs basically hidden behind this. We can inspect this mapping. This is a setting in the configuration of your domain. I'm going to use ADSI edit to inspect this. So we connect to the configuration of our domain and then specifically have a look at the directory service node. And in the properties, we'll inspect the SPN mapping attribute. Now within this SPN mappings attribute, you can see that the host SPN, as I mentioned before, actually maps to a whole list of other SPNs, so it's quite extensive. So we can see whenever a host is configured, that actually means there's also www, HTTP, IAS-admin, CIFS, and various other SPNs that are implicitly then configured via the host SPN as well on this system. Now, a bit more details about the keys that are involved in Kerberos. As we've learned before, we have secret or long-term keys and session keys. And these are all, as mentioned already, purely symmetric, used for symmetric cryptography to establish trust between the parties and the secure communication channels. The secret key is also known as a long-term key, which is shared between the users or the services and the KDC. So the user has their key and the KDC knows the key as well, or the same for the services. And this is mainly used to authenticate the individual parties so that the KDC knows, is it the right user, is it the right service that it's talking to. And the secret key is not directly the password of the individual account, but rather it is derived from the account's password. So that could be the password of the user or the password of the service account that is associated with the SPN. How it is derived is specified, or depending on the encryption type that is used. We have a few different encryption methods available in Kerberos. That could be AES-128, 256, or RC4, for example. And within each standard of these encryption algorithms, there is a so-called string-to-key function defined, which defines how this secret key material can be derived from the user's password. For the session key, those are also known as the short-term keys or secrets that are shared between individual users and services to secure a specific communication session, and they are generated on the fly by the involved parties, so they are not pre-established or predefined. Let's look at some examples. When we create a new domain user, we first define the password of that user, and then the domain controller automatically derives all the different forms of secret keys, so AES-128, 256, RC4, and so on, and stores them within the domain controller's database. And when you log in on your client with a domain user, the same thing happens as well. You provide the password, and the client then derives the Kerberos key material and stores it temporarily in the ELSA's process memory. Here are a few examples of how these keys look like. Here we have 4 different variations. We have the anti-hash, which is the same as the user's password as it's stored in Windows. This is used for RC4 encryption. And then we have AES-256, 128, and even DES. Few more details about the tickets that are involved in Kerberos. The tickets typically carry identity information about a given subject. So that could be who's the user, what groups is he part of, and so on. And a ticket is always intended for a very specific audience, so a service that consumes it or receives it and gets information out of it. If we look at tickets, we will see that certain parts of tickets are actually encrypted. And the encryption is either based, depending on what kind of ticket it is, with the long-term secret, so the password hash or the Kerberos keys, or they are encrypted with these temporary session keys that are established between 2 communicating parties. Ticket types, there are two of them. Once we have the ticket granting ticket, which is essentially used to confirm the user's identity towards the TGS service, so the ticket granting service of the KDC. And then we have the service ticket, which confirms the user's identity towards a specific service. So for example, if we access a file share on the system FS1, we use or we request a specific service ticket to access that service. A bit about ticket inspection on Windows. I'm again back in the test environment here, or lab environment, this time on a client, and we can simply use PowerShell to inspect the tickets that we currently have on a user. We can see we are logged in as a domain user called T Massey or Trevor Massey in this case, and we can then use the command klist to inspect the tickets that are present in our logon session. In this case, we have 5 tickets, so the user has already been active for a while, accessing some services, and then the tickets are cached for a while. For all of the tickets that we have here, we can see who they are intended for, so who will consume them, so the krbtgt service, or LDAP, or CIFS, and so on. And we see some other information like lifetime of the ticket, encryption algorithm, and some flags that essentially govern how the ticket is used. Let's look at one specific instance. We'll pick this ticket here. We can see that it is a ticket issued for a CIFS, so file share on DC1. So whenever we access the file share on the domain controller, we use this ticket to essentially authenticate ourselves. And we can see that the ticket is issued for our user, Trevor Massey in this case. Now let's look at a very high level on how Kerberos actually works under the hood. What happens when we first access a service? What are the messages that are exchanged? We can see the different participants in this authentication process. On the left side, we have the user that wants to access a resource. In the middle, we have the KDC split up into the two logical components, the authentication server and the ticket granting server. And on the right side, we can see the resource that we essentially want to access. Now, first on the client, we have to log in, of course, and then we, as a first step, request our TGT from the authentication server, which then identifies us for the rest or for the next request. For this TGT request, if everything is correct and the server validates or can validate this request, it will return a TGT to us, a ticket granting ticket. And with that ticket granting ticket, we can then perform the next step in the Kerberos Authentication Flow, where we go to the ticket granting server and now ask for a specific service ticket for the service that we want to access. So in our case, we request a service ticket for a specific SPN, namely the SPN CIFS on foo local, which will be the SPN registered for the file share service over here. Along with this request, we also send our TGT as a way of proving our identity to the ticket granting server. The ticket granting server will then evaluate the TGT, and if everything is in order, it will return the requested service ticket. Now, there's one important thing to notice about this step here. The decision whether we are allowed to effectively access the file share over here is not taken by the ticket granting server. So we will always get a service ticket for the service we requested, no matter whether we are actually allowed to access it or not. The service ticket simply serves to authenticate us towards the target service, and the target service then itself will take the decision whether we are allowed to access it or not. So this step always works no matter what kind of service ticket we request. Now, once we have the service ticket, we can then present this to the actual target service, so the file share CIFS service running on foo.local in this case. And as mentioned before, this system will then inspect this service ticket, look at who we are, and then based on that information decide whether we are allowed to access or not. And then, of course, if we want to access a different service, not sys on foo.local, but let's say LDAP on the domain controller, or a database on a different system, all these steps here are simply repeated. So we still use the same TGT for its lifetime, which is by default 10 hours. And within those 10 hours, we can use this TGT to simply repeat this process for every new service that we want to access. To get a bit of a better understanding on how Kerberos works, it is quite useful to look at it on the network level, and for that Wireshark is the right tool because it already has a built-in dissector for Kerberos. So that means the Kerberos protocol or the data structures are presented in a way that we can easily inspect it, and so they are automatically reconstructed, and we can dig into the different levels of the message. One nice thing to know is that in Wireshark you can simply filter for Kerberos, and the filter will actually capture messages that are either the Kerberos protocol itself or whenever Kerberos is used wrapped into another protocol. So for example, SMB, which we'll see in the demo right after this. So now let's look at a practical example. I'm back in the lab environment. I've set up a Wireshark instance with a filter set to Kerberos. And before we start, we clear our current ticket list so we can start from scratch. So we have no tickets in cache now. And to actually trigger the Kerberos flow, we simply try to access a file share within domain. And we can see as a result, we have now all the messages captured within Wireshark. I have put up the high-level authentication flow that we've seen on the previous slides as before, so we can try to match what we see in Wireshark with the diagram in the lower half of the image. Let's start with the beginning. We see two specific messages that are related to a mechanism called Kerberos Pre-Authentication. We'll look into that in a few slides. So for our purposes now, we can simply start with the message on frame 1190, which is the AS-REQ, so the request for a TGT from the authentication server. Followed by that, we have the AS-REP message, where we get the TGT back from the authentication server, and then afterwards use that to request a service ticket from the ticket granting server in a message called the TGS-REQ. So that will be this part. This is then answered with the TGS-REP containing the service ticket sent back to a client, and then eventually we will present that service ticket to the file share that we want to access. Now you might notice that here the protocol changes. We don't have Kerberos anymore, but rather SMB, and the reason for that is that SMB uses, in our case, Kerberos under the hood to authenticate the user towards the server and the other way around. So we just see that Wireshark has captured SMB packages here that contain Kerberos data structures. Now, if we look into a bit more into details on what we can inspect in the Kerberos messages in Wireshark, we can then see that some parts of, as we've learned before, of Kerberos messages are actually encrypted with either session keys or long-term keys, and we will not be able to look at the content of them. However, as you might have seen as well with TLS connections, Wireshark is able to actually decrypt those parts if the correct keys are provided to it, and in Kerberos this is called a Keytab file. We can load that into the configuration of Wireshark, and then it will attempt to decrypt all the messages that are encrypted with the provided key material. We can have a look at that in or the encrypted version as well. We dive a bit deeper into one of the packages we recorded before, namely the TGS-REP. So we get the service ticket back from the TGS of the KDC. If we look at this message in Wireshark, we can then see that we have a Kerberos layer, so to speak. This is the dissector that I mentioned before, which allows us to dig into the structure of the Kerberos message. So we see here we have the TGS-REP, which contains some information. Some of it is plain text. For example, we can see the client name. So the ticket was issued for Trevor Massey in this case. And then we can also see that we have further data structures like the ticket, which again contains some plain text information like the target, principal name, who was this ticket requested for. Here we can see this is a ticket for the CIFS service running on FS1. So this is directly the result of us trying to access the file share in the Explorer. But then we have finally the encrypted parts of the ticket. So two of them in this case, and as you can see, both are just ciphertext and we will not be able to access the content of them. To create the Keytab files that you can then actually load into Wireshark to decrypt the Kerberos traffic, there are multiple tools available. So on Unix, you might want to use ktutil or ktbus on Windows to create a Keytab file for a specific user. For that, you will have to provide the password of that specific account, so and some additional details like the domain name and so on. So the Kerberos key material can be created from that. After that, the Keytab file then contains all the long-term keys of that user, so all the different variations for the encryption algorithm that might be used. Now, for demonstration purpose for these video series, it is also possible to create a Keytab file for all accounts within the domain, which will then enable you to see and inspect all the Kerberos, and for first and foremost decrypt all the Kerberos messages that are exchanged within the domain. There are multiple tools available to do this. For example, you might use the Forest Trust tools by Dirk-Jan Mollema, or also the Samba tools available on most Unix distributions. Now, one remark before we actually jump into the demo of creating a domain-wide Keytab. It's important to notice that it's generally not a good idea to do this on a productive environment, since you will be extracting all the secrets from your domain controller and storing it in a file somewhere else. So there's a higher risk of leaking those secrets. And this goes without saying, this should not be done on a productive environment. However, in a lab setup, it is totally fine and helps you really understand the finer details of how Kerberos works. So let's create a domain-wide Keytab file in our lab setup. I'm on my Kali machine, which is in the same network as the domain controller, and I'm going to use the Samba tool to create this Keytab file. The first thing we have to do is essentially to create a replication of the DC database. So we have to clone the whole database for our domain, which will be the child.testapp.local for our test setup. And we have to specify some additional options on where to put the whole configuration or the clone output, that we want to include the secrets, so the key material, and then we also have to point the tool to the domain controller, since this machine is not domain joined. Lastly, we need to specify a user with the right permissions. In this case, this is a domain admin account, since we are essentially doing a DC sync, which is only available to domain admins without additional configuration. We have to provide the password of the user, of course, and if everything goes well, the tool will start synchronizing or cloning the database and the configuration of our domain. Now, for our small domain, this should go quite quickly. For a bigger setup, you might have to, it might take a while. And once the whole configuration has been cloned, the next step is then to simply put the information into the right format or structure so it can be used as a Keytab. This can be done with the Samba tool as well. There is a specific command to export the relevant or necessary information in a Keytab format. We can provide a name and point it to the config that we previously extracted. And after this step, we have a Keytab file that can now be used read into Wireshark. We're going to have a quick look at it with this command, and we can see that we now have for all the principals within our domain the respective secrets listed in a structure format, in a Keytab format. So, for example, for this first user here, we have multiple entries, as you can see for the others as well. In this case, those entries correspond to the different encryption types that might be used in Kerberos. Remember, depending on the encryption type, the key material is derived differently. So we have RC4, we have AS-128, and we have AS-256 as well. And this then goes on for all the other principals in our domain, so users and machine accounts as well. So now that we have created the domain-wide Keytab file, we can load it into Wireshark. Once we have done that, all the messages, Kerberos messages, will be decrypted. This works even for messages that have been recorded previously, unless, of course, the associated passwords and therefore the key materials have changed between the time of recording and creation of the Keytab file. If we look at the output of Wireshark after we have loaded the Keytab file into the configuration, we will see that certain parts of the messages are now highlighted in blue, and this essentially tells us that Wireshark was able to decrypt some parts of these messages. The nice thing about how the dissector of Wireshark does this is that it also will tell us what key material has been used to decrypt this specific part of the message. So, for example, here we can see that to decrypt this cipher string here, Kerberos has used an entry of the Keytab associated with the principal DC1$, so that will be the machine account of DC1. The same thing goes for session keys, so keys that are generated on the fly. Whenever Wireshark encounters a message that has been encrypted with a session key, it will tell us that it has used a key that it has learned in some previous message. So, for example, the key to decrypt this cipher string here comes or was learned in frame 556, which refers to a previous message recorded in Wireshark. And then whenever a part of a ticket contains a new key, which is the case here, Wireshark will automatically add this key to its repertoire and have it available for decryption of later messages. Let's look at that in practice. We go back to our lab, and I have copied over this Keytab file that we have created previously. And in Wireshark, we can then load that into the settings. So you go to preferences, on the protocol, you jump to KRB5, and here you can then provide the Keytab file that we've created previously. Don't forget to tick the box to try to decrypt Kerberos blobs, and then apply or click OK to load the Keytab file. And you will see that it changes or applies automatically. So now Wireshark has already decrypted all the information within the tickets that we have recorded. You can see the blue highlighting, and we can actually have a more detailed look at it when we go into the structure of the message. Below the message, you can also see a summary of what keys were used and what keys were learned from the message. Now, if we go back into the TGS-REP, we see those encrypted parts again, the cipher where we couldn't look into before, but now you will be able to dig down deeper into it and actually have a look at the encrypted part of the ticket. In this case, this contains a key, and Wireshark would then automatically add this key to its repository, let's say, and be able to use it later on in when decrypting other messages. Now, let's dive a bit more into the details about how the protocol actually works. So we've seen a high-level overview so far, but now we want to go step by step through the different messages that are exchanged between the parties and look at how Kerberos actually achieves mutual authentication and this establishment of session keys between the parties. For this, we'll look at each message one by one, and also then every explanation is followed by an inspection in Wireshark, so you get a real-life view on what actually happens. So first, we've learned that it all starts with a so-called AS-REQ, where a user goes to the authentication server and asks for a so-called TGT. Now, for this TGT request, we have to send some information. First of all, our user ID, what service that we want to talk to, and for TGT requests, this will always be the krbtgt account. And we also send along some pre-authentication data. Pre-authentication data is essentially the current timestamp encrypted with our password or our secret key. And we'll have some more details on this on the next slide. Along with that, we can also request a specific TGT lifetime and some other metadata, but that's about all the information that we send to the authentication server. Once the authentication server retrieves our request, it will look up the user ID that we specified and check if it can find our user in the KDC's database. From there, it will be able to retrieve the secret key derived from the account's password, and with the secret key, it can verify the pre-authentication data. So it can essentially decrypt it and look at the timestamp and see if it's a fresh message. Now, some more details on the pre-authentication feature. We've already learned that to request a TGT, in general, we must be authenticated, so we must prove to the KDC that we are the right user, or we are in possession of the user's password, and this is called Kerberos pre-authentication. The process for this is quite simple, that we just our client takes the current timestamp and encrypts it with the user's secret key. This encrypted timestamp is then simply added to the first request, so the AS-REQ that we've talked about previously. And when the KDC receives this request, it can extract the encrypted timestamp, try to decrypt it, and verify if it's a fresh message. If that works, the KDC knows that the user, first of all, has the correct password associated with that user account, and that this is not a replay attack. Now, it's good to know that pre-authentication is enabled by default for all users, but you can actually disable it, either for one or for all users within your domain. However, be aware that this opens you up to a vulnerability called AS-REP roasting, and we'll be looking into that in a later part of this video series. So the recommendation from now is don't disable Kerberos pre-authentication unless there's a specific need for it. The Kerberos pre-authentication feature can also be seen in Wireshark. We again back in our lab environment with the Kerberos messages that we've recorded previously. And if we look at the very first request, we can see that this is indeed an AS-REQ, but there seems to be an error afterwards, and we'll explain why this is the case. If we look at the first AS-REQ message, it will be obvious that our client tries to request a TGT without actually performing any form of authentication. So the PA data structure within the request, the pre-authentication data, simply contains some flags and configuration data, but not actually any authenticating information. The KDC in turn then simply replies with an error and instructs us that for our user account, so for Trevor Massey, pre-authentication is required, and essentially asks us to repeat the AS-REQ request, but with authentication information included. This is exactly what our client will do. So we now see the PA data structure now contains 2 items. We still have the same configuration information as before, but we also have this encrypted timestamp information. Now you can see that this is already marked blue since Wireshark has taken key material from the Keytab file, specifically from our user Trevor Massey, and decrypted the timestamp that we sent along to prove that we know the password and that this message is recent. Once we have completed the AS-REQ step with successful pre-authentication, the server then will send us back the requested TGT or ticket granting ticket. This essentially consists of two parts. So first of all, we receive back a so-called session key. The session key part of the message is encrypted, most of it, with our own client secret key. So here in this case, it's Alice that requested the message. So this part of the message, or the TGT, so this part of the message will be encrypted with the secret key of Alice. And secondly, we will also get the actual TGT, so the ticket granting ticket. We have some readable information in there, but most of the ticket is encrypted with the secret key of the target of this ticket. Then the target, the receiving or the recipient of this ticket eventually will be the TGS, so the ticket granting service, which is operated by the krbtgt account. So this part of the message is encrypted with the secret key of the TGS service. What our client does then is it will first load or fetch our secret key from our user from the LSAS process. And with that secret key, it will be able to decrypt part A of the message, the session key, and extract this session key from it. Now you can see that the same session key is also present in the TGT, but since this data structure here is completely encrypted with the secret key that we do not possess, or our client does not possess, we cannot essentially look into this part of the message. We will simply hold on to it for later use. Let's look at the AP or AS-REP in Wireshark. If we drill down into this message, we can see that we have essentially those two data structures that I just mentioned, besides some clear text information like who the client is, so Trevor Massey in our case. And then we can see that we have the ticket and the encrypted part, which is the session key. Let's first have a look at the ticket itself. So the ticket has some clear text information that we can directly read without providing the key material. Mainly we can see who the ticket is intended for, so that will be krbtgt, so the operator of the TGS within our domain. And then we have the encrypted part, which we can now look into because we provided Wireshark with the key material. If we open up that, we can first see that who or with what key material this ticket was encrypted. In this case, it is indeed the key material of the krbtgt account, so derived from the password of this account. And within the encrypted ticket, we have then, as we've seen on the slide before, we have the session key and some other information like timestamps, the name of the client, and so on and so forth. Let's look a bit more into the key, the session key. We see that Wireshark automatically adds this key to its repertoire, and we will also take note of that. So in message 1192 of our recording, we have learned the key E250B348. We'll just note down the first few characters, and the purpose of this key is essentially a session key for the communication between our user, Trevor Massey, and the krbtgt on DC1. Specifically, it will be consumed by the ticket granting service of the KDC. Now let's close the ticket and look at the second part, which is the session key that is encrypted for our user. If we open up that, we again can inspect the cipher and see that indeed this part of the message is now encrypted with the key material of our own user, so of Trevor Massey. If we go down into it, we can again see some meta information like lifetime and so on, and we'll see the same key again. So this is again, if we look at the key, the beginning, it's the same key as we've seen in the ticket itself. So with this, we have once the session key in this data structure and once the same session key in the ticket. So both parties will then have the same key available. Now that we got our TGT, we can go on to the next step of the Kerberos Authentication Protocol, which is the TGS-REQ, where we go back to the KDC, present our TGT, and ask for a service ticket for a specific service. So in the TGS-REQ, we send along the TGT that we received previously. This is an exact copy of it, so we don't change anything in because it's encrypted. And we send along the information on what service we would like to access. So that could be CIFS on FS1, that could be MS SQL on another system, and so on and so forth, and some other metadata. Now, along with that, we also send a so-called user authenticator. The user authenticator is a very simple data structure. It is essentially our user ID and the current timestamp, which is then encrypted with the session key that we have previously established and that we use to communicate with the ticket granting service. Now you can see that the TGS session key that we use to encrypt the authenticator is the same that is contained within the actual TGT, and that will make sense in a few seconds. If we look at what the server does on its end when it receives this message, first of all, it will look up whether the service principal that we request is actually registered within the domain, otherwise we'll get an error. If this is the case, it will load the secret key of this of the service that we request. It will then decrypt the TGT that it received with its own secret key. Since this is the ticket granting server, it has access to its secret key. So it will decrypt this message here, and from this message it will learn the session key that is used to secure the communication between our user, Alice in this case, and the ticket granting server. From here, the TGS or the KDC will be able then to decrypt message D, the user authenticator, because this is encrypted with this session key, and then validate its content. So look at the user ID, does it match whatever is contained in the TGT, and is the timestamp fresh enough? In Wireshark, we can also look at the same things. So again, we drill down into the Kerberos data structure from the TGS-REQ message, and within there we can see that we have different parts again. As before, we have a so-called PA data, the pre-authentication data, but now this is not simply a timestamp encrypted with our password, but this actually includes now the ticket granting ticket. So we use the ticket granting ticker as a way of assuring our identity and proving who we are, that we are who we say we are. So we send along the ticket. That's what we've seen before. This is just a one-on-one copy of the TGT that we got previously. We can see that it is encrypted with the key material of the krbtgt account, and besides the ticket we also send along the user authenticator. And again, this authenticator is simply the username or the user ID and a timestamp, which is then encrypted with the session key that we have exchanged previously, and we can see that in Wireshark as well. If we look at the key that is used to decrypt this message, it comes from frame 1192, and if we look up in our table, this is the key, the session key that is used to secure the communication between our client and the krbtgt or TGS in this case. Next, when the KDC has processed our request, it will reply or issue a service ticket back to us. So in this message, it's essentially the same as we've seen before. We get back again another session key, which is wrapped or encrypted with an already pre-established session key, the session key between our client and the TGS, and we get back a service ticket. Now the service ticket itself is encrypted with the secret key or the key material of the target service. So if we request a file share service on FS1, for example, this will be encrypted with the secret key of FS1, of the account of FS1. And the service ticket itself again contains user ID, timestamp, the authorization data, we'll look into that later, and a new session key. Now this session key is intended to secure the communication between our user, so in this case Alice, and the target service that we want to access, which would be the file share. If we look at the session key message part, we can see that we have the same service session key in here as is contained within the service ticket. And this part of the message is encrypted with the session key between our user and the TGS. So when our client gets back these messages, we can decrypt the session key message because we already know the session key from the previous exchange, and therefore then retrieve the service session key from it. Again, as before, we cannot really do anything with the service ticket since it is encrypted with a service key that is not accessible to us. It can only be decrypted by the receiving service. So we'll just hold on to that for the next message. In Wireshark, we can again inspect the details of this message. So we have the TGS-REP message opened in Wireshark. We dig down into it and we can again see some plain text information. Again, this is intended for a user, and then we have the ticket and the encrypted part, which is the session key. The ticket itself, if we open that, we can see what the audience of the ticket is, so who is it intended for. That will be CIFS on FS1, so the file share service. And in the encrypted part, we can see what key material was used to encrypt it. We have again some plain text information in it and a key, a session key, and encrypted. It was encrypted with the key material of FS1, so the target service that we want to access. And then we have a session key, a new session key in it. So let's take note of that. So in frame 1203, we learn the session key A92 FEA97. And this is a new session key. And the purpose of this key is to secure the communication between our user, Terramasi, and the actual target service. So CIFS on FS1. Besides the ticket, we have, or within the ticket itself, there's also one thing I want to highlight here. This is the authorization data. The authorization data is essentially a data structure that contains information about our user, which is then used by the target service to make authorization decision. You can see it's quite nested, but eventually we will end up at the information about our user, like logon time, group membership, and so on, but we'll look into that later. Now, besides the ticket, there's a second part in the message, which is the session key that our user or our client needs to retrieve. If we open that up, we can see that it contains a key as well, and it was encrypted with a key that we learned previously. So that was exchanged between the parties in frame 1192. This is the session key between the user and the KDC. And the key itself is the same as we have already seen in the ticket above. So it's also A92FEA97. So again, we have the same session key present in the ticket and in the session key part of the message. So both parties then eventually will have access to the same session key. Now, once we have completed this step as well, it's finally time to actually connect to the target system. So that will be the service, so file share, for example, that we want to access. And this part of the Kerberos flow is called the AP-REQ. In the AP-REQ, we send along the service ticket that we received previously, exact copy since it is encrypted, and again, a user authenticator. So this is a repetition of what we've seen before when we requested the service ticket. Now it's just targeted toward the actual service that we want to access. Again, if we look at the service ticket, this has not changed. It is still encrypted with the secret key of the receiving service, and the authentication on the authenticator is essentially the same again. We have the user ID and the timestamp. Now this time it is encrypted with the session key that is associated with this service ticket. So there's a relationship between those two messages, and if the service, or when the service receives those messages, it will, since it has access to its own secret key, it will decrypt the service ticket and from there fetch the service session key, among other things. It will then decrypt the user authenticator message with the service session key, and we will be able to validate the authenticator. So is it the same user as is contained in the service ticket, and is the timestamp fresh? And then the service will also look at can look at the authorization data. I can extract it from the service ticket, look at the group memberships of the user and other attributes, and based on that decide whether or not the user should be granted access. Now, this is not strictly part of the Kerberos protocol, so you won't see there's no implementation for that. This is part of the application that processes this request. In Wireshark, we can also look into that. Now, as mentioned before, this is now not labeled as Kerberos protocol, but rather in our case, it's SMB2, since we have tried to access a file share. So we'll see the SMB2 protocol here. As long as Wireshark can decapture it, it will figure out that this protocol contains somewhere deeper down a Kerberos as authentication mechanism, so it will still be captured by our filter. Now let's dig down into the protocol until we arrive at the actual Kerberos message. It's quite a few levels down, but eventually we'll see that we have indeed an AP request Kerberos message. In the AP request itself, if we dig into that, we can see the two parts that we have mentioned before. Once we have the ticket itself, and the authenticator. If we open the ticket, we can see that it was encrypted as we've expected with the secret key of the recipient service, so of FS1 in this case. And now in this case we have a session key, again the session key that is used for the communication between our client and the user. And then if we look at the authenticator, we can see that this was encrypted with this session key that we just talked about, as we've seen on the slides before. So the recipient service will be able to decrypt that and verify that everything is in order. And now in this case, we have a bit of special content as well. We have a so-called subkey. Now the subkey that you can see a bit further down after the other information is optional. This doesn't have to be present. In this case here, it is part of the exchange, and the subkey essentially is a key generated by the client, which is then processed by the server and used to secure the actual communication. So it's not the session key that is then used to secure the SMB communication. The session key is just used for the Kerberos part, but they actually agree on a different key for securing the SMB traffic. We'll take note of that as well. So that will be the key F563E1C. And this is, as mentioned, a subkey which is generated by our client and sent to the server as part of the authenticator. Then finally, when the service receives our service ticket, has decrypted everything, has taken the authorization decision, and in our case now allows us access, it will complete the Kerberos authentication flow with the AP-REP message. The AP-REP message is quite simple. It simply contains an authenticator, not this time for the service, to conclude the mutual authentication. It is simply the timestamp and service ID encrypted with the session key negotiated between the two parties previously. So when the client receives this message, it will load the service session key, decrypt it, and verify if the ID and timestamp is what it expects to be. And at this point, both parties are mutually authenticated. They have knowledge of a common session key or even multiple keys. Remember, we have this sub key as well. And then they can start, based on these keys, interacting over a secure channel, ideally. So the actual protocol that we requested, that could be SMB or HTTP or LDAP or whatever was requested. Let's look at the last part in Wireshark as well. So the AP-REP, as before, this is part of the SMB protocol in our case, since we tried to access a file share. So again, we have to dig down through the different SMB packet layers until we arrive at the Kerberos structure. We can see, as we expect, this is an AP-REP message, and it simply contains an encrypted part, which is the authenticator sent back by the server that we try to access. If we look at how this is encrypted, we can see that the encryption took place using a key that we learned previously in frame 1203. If we look that up in our table, that matches with the session key that was previously exchanged between our parties. So the authenticator is, as we've learned, encrypted with the session key. Our client could then decrypt it, look at it, and see essentially the timestamp, see that it's fresh. And in this case now, because we have already sent a sub key from a client to the server will also reply with a sub key. Now this is a new sub key based or derived from the sub key that the client sent. This is just according to the specifications. We can take note of that. That will be the key 2C978105. And as mentioned, this is a sub key now generated by the server, but is based on the sub key that was sent by the client. And then this key can actually be used to secure the actual communication. Now that we have seen all the individual parts of the Kerberos authentication flow, let's look at it again in the big picture. We have the same situation as before. So on the left side, we have our user Alice, and on the right side, we have a resource that we would like to access, for example, a file share running on foo.local. In the middle, we have the KDC split into the authentication server and the ticket granting server. Now, initially, we also have some keys that are already pre-established. Specifically, Alice has access to her own long-term key material derived from her account password. And on the right side, the server has access to its own respective key material as well. And the KDC, since it is running on the domain controller, has access to the key material of all involved parties, namely in our case, the key of Alice, of the target server, and of its own operating account, which is the krbtgt account. To initiate the Kerberos authentication flow, Alice will now, as a first step, send the AS-REQ message. The AS-REQ message simply includes the pre-authentication data, which, as we've learned before, is a timestamp encrypted with the key material of the user. Now, in all the messages that we are going to see in this slide, the color of these boxes always represents the encryption key that was used to encrypt this part of the message. So in our case, this matches with the key of Alice. Now, when the authentication server receives the AS-REQ, it will first verify the pre-authentication data, since it also has access to the same key material. And then it will generate a session key. This session key is specifically used to secure the communication of the next step. So that means between Alice and the TGS. Then it will also create the TGT. As a reply, it will send the AS-REP part of the protocol flow. The AS-REP part, first of all, contains the TGT, which inside of it has this session key. The TGT is encrypted with the long-term key of the KDC. And besides that, we also have the session key, which is encrypted for Alice. So this is the same session key in both parts of the message, once encrypted for the TGS and once encrypted for Alice. Now, when this message is parsed, Alice will be able to extract the session key from this part of the message, and this session key is then available in Alice's logon session. Next, Alice will generate an authenticator. The authenticator is simply username and the current timestamp, and the authenticator will then be encrypted using the new session key. The next part of the protocol is the TGS-REQ message, which is sent to the TGS. It will include the TGT itself, so this is a one-on-one copy of this TGT that was received previously. And besides it, we also have the authenticator that we just created. The TGS, upon receiving this message, will be able to extract the session key from the TGT part, since the TGT is encrypted with its key material. So it then has access to this session key for further parts of the communication. Then it will verify the authenticator, since it now has access to the corresponding key. It will generate a new session key, again, for the next part of the communication, specifically for securing the communication between Alice and the target foo.local. Lastly, it will also create a service ticket and then pack that all up together into the reply, the TGS-REP message. The TGS-REP message includes the service ticket, which includes the session key. The service ticket is encrypted with the key material of the target account, so that will be the long-term secret of foo.local. And alongside, we also have the session key that was generated just now, encrypted with the session key established in the previous step. So that will be the session key between Alice and the TGS. This message is then parsed on the side of Alice. Since we have already access to the encryption key of this part of the message, we can extract the new session key from it and make that available in the logon session as well. Then we create again an authenticator, so this is essentially a repetition of the steps before, and then send along this data in the AP-REQ to our actual target. The AP-REQ message contains the a copy or the exact same data structure of the service ticket, which inside of it has the session key for this part of the communication, and in addition the authenticator that was created. Now the target service has access to its own key material, can decrypt the service ticket, and from there extract the session key. And with the session key, the target is then able to verify the authenticator, since this was the key used to encrypt this part of the message. As a last step, it will create its own authenticator and simply encrypt that again with the same session key and send this back to Alice. Now, once this step is completed and everything is in order, we arrive at a situation where both parties are mutually authenticated and have exchanged key material that can then be used to secure the communication. On previous slides, we learned about the authorization data that is contained within Kerberos tickets, and specifically the authorization information is present in both ticket granting tickets and service tickets, and it represents a collection of information about the user that is contained within the ticket. Now, the information specifically is held in a so-called privileged attribute certificate, or PAC for short. And within those PAC, you find user information itself, so essentially the name, profile, information about the home directory, logon scripts, and so on. Information about the account itself, so whether the user has recently entered a bad password, when the last logon took place, the last password change, and some other information that might be relevant when you do make authorization decisions. And lastly as well, the group membership information. So what groups of the Active Directory is the current user a member of. Now, when a service receives a ticket, they can then inspect the pack to essentially perform authorization decisions. So they can look at the information within the pack and then decide whether or not the user should be allowed to access the resource in question. And all of this can take place without reaching to the domain controller to fetch this information, because it is already present in the pack. Now, it's also good to know that the pack is signed by the KDC. There are multiple signatures present. One signature is intended for verification by the receiving server. So the signature is made with the key material of the server. And then there's also a signature with the key material of the KDC itself. This signature by the KDC is specifically intended for when the service wants to perform an additional verification on the pack, because there is a mechanism called KRB-verify-pack that allows the service to forward the signature of the pack that it currently is inspecting to the KDC for an additional validation step. It's also good to know that this validation step is only performed in very specific cases. Microsoft has provided documentation for this that go into detail on what the decision logic is for this, but essentially for services or for processes that run as a service in the context of local system, local network accounts, and so on, or have a specific privilege that allows them to act on behalf of the operating system, this validation step is usually skipped. Now we can inspect the pack information with different tools. I'll show you two examples in this case. First, we'll request another ticket. In this time, we use Rubius. I'm back in the lab environment where I have Rubius on the machine, as well as Wireshark set up with the Kerberos filter. So first, we'll use Rubius to request a ticket granting ticket. For this, we have to provide our username as well as the password. And with that information, we will be able to request a TGT from the domain controller or for the KDC. Now we can see as a result, we have this base64 encoded blob, which is essentially the TGT that we got back. Let's go to Wireshark first and look at what we received. So we issued an AS-REQ and got an AS-REP in return. And as we've learned before, in AS-REP, there is the TGT included, this ticket data structure. And since we have loaded the Keytab file into Wireshark, we can actually look at all aspects of this ticket. So let's look at the pack in a bit more details. We can open the ticket, go to the encrypted part. We see that this ticket was encrypted with key material of the krbtgt account, as we've seen before. And then if we go further down into it, we can find the authorization data structure, which is nested over a few levels. Eventually, we will end up at the logon info structure that contains all the information about our users, or Trevor Massey in our case. One level further down, actually two more levels, and we see the actual data. So we see when the user has logged on, when it has logged off the last time, when was the password changed the last time, what's the account name, do we have any logon scripts configured, where's the profile path, where's the home drive, how many times have we logged on, did we have any bad password attempts, what's our user ID, the group IDs, so which groups are we member of, in our case that will be domain users, and lots of other information that are associated with our account and can be used to make authorization decisions. So this is how this data, the pack information, is represented in Wireshark. However, we can also look at it in another way, and we can use in-packet tools for that. So for the in-packet tools, we need to copy over the ticket to our system. Now, it's important to know that this base64 content that we have here is actually the ticket and the session key with it. So we can copy that over and use it fully on another system. So on our Kali Linux, we create a new file, paste the base64 encoded content into it, and then first we have to decode it to be able to parse it with the in-packet tools. So we'll simply base64 decode it and write it to a file called tgt.kerb. And then we can use the first tool of the in-packet suite called in-packet ticket converter, which will transform the ticket from one format to the other, specifically in our case from the Kerberos format to the so-called C-cache format, which can then be used with the other in-packet tools. Once this conversion has been done, we can use the next tool called in-packet describe ticket, which will allow us to inspect what the contents of this C-cache file, and we can see that we are presented with a nice view of the information present within this ticket. So we have the username, the realm, when the ticket was issued, when it will expire, the flags, the encryption method. We also have the key, since the session key is part of this base64 blob, or was part of this blob as well. If we go back to Wireshark, I can show you what I mean with that. As you know, the AS-REQ part contains two messages, essentially, the ticket and the encrypted part with the session key, and both of these data structures are contained within the base64 blob. Now, we don't see the pack here, and the reason for that is that the ticket could not be decrypted since we didn't provide any key material, and the pack is part of the encrypted data. If we look at how this data was encrypted, so what key material was used, we can see that it was the key material associated with the krbtgt account. Now we actually have this key material since we created this domain-wide Keytab file, and we can simply look up the key associated with the krbtgt account within that Keytab file. Let's see if we can find it. So we're looking for the krbtgt account. There's multiple of them, so we have to pick the right one in the child test lab local domain. So the key would be this here, beginning with 579F4. Remember that, because we can verify that this is actually the right key. If we go to Wireshark, we can see that indeed F79F4 was used to decrypt this message. So we can provide this key material to the describe ticket tool of in-packet, and as a result it will be able to finally decrypt the whole ticket. So besides the information that we had before, we can now also see all the contents of the encrypted part, namely the privilege attribute certificate, or the pack containing the information that we've seen before: log on time, log off, password information, user ID, group memberships, and so on and so forth. So far on our journey, we have talked quite a few times about this krbtgt account. So let's look into a bit more details of regarding this account. The krbtgt account is essentially a built-in account in your domain that is used to operate the KDC services, so the authentication server and the ticket granting server. And the key material of this account specifically is used to encrypt the ticket granting tickets. Furthermore, it is also used to sign some parts of the message for integrity verification, specifically the checksum of the privilege attribute certificate. The account itself, as you can see, is disabled by default. It cannot be activated as well, so it's not really a usable user account in that sense. The account's password itself is also a bit special since it's generated randomly when you set up the domain, so it's not necessary to specify this on your own. And the random generation also helps with making sure that this password of this account cannot be brute forced, which would lead to the compromise of the account itself and the associated KDC services. Now, you might ask yourself, what happens if this account is compromised eventually by an attacker? And essentially, this grants full control over the whole domain. Such an attack requires already high privileges within the domain, since you need to somehow get access to the key material of this account, which is only held on the domain controllers. So most likely this happens via a so-called DC-sync attack, which typically requires privileges or equivalent of a domain administrator or a domain controller, or some specific privileges that are sometimes set for an Active Directory sync account. So when you synchronize your users to Entra ID, for example, you might have other accounts in your environment that can perform a DC sync attack. Now, why does this is this equivalent to full control over the domain? Remember that the keys, the Kerberos keys of this account, are used to create, assign, and encrypt ticket granting tickets. And if you, as an attacker, have access to this key material, you can essentially do the same and craft your own ticket granting tickets and write into them whatever you like. So you can impersonate any user against any service, essentially. This is known as a so-called golden ticket attack, because essentially it grants you access to all the resources within the domain. What's also interesting to know is that these golden tickets, so the ones you create yourself, they can essentially have an arbitrary lifetime. So you could choose to have a ticket that is valid for 1 year, for example, and therefore this would grant an attacker extended access over time, unless those tickets are somehow revoked or the passwords are changed for this account. In contrast, when you compromise a service account, so any account that has a service principal name registered to it and operates a service within this Kerberos realm, and you get access as the attacker to the Kerberos keys or the credentials of this service account, you can then forge tickets for this specific account or for this specific service only, and this is then known as a silver ticket attack. Since this krbtgt account password is so essential to the security of your domain, it is good practice to change it regularly. This is a recommendation also given by Microsoft. Essentially, they recommend to change it twice a year or even more. However, there are some caveats to that. So first of all, you need to have a functional level of Windows Server 2008 or greater for this to work. And you have to take some specific measures when changing the password. There's an extensive knowledge article about that where you can find more details. But essentially, the main thing to keep in mind is that the password has to be rotated twice since and within a short amount of time, since the KDC also keeps track of the previous password for basically to rotates two passwords for a rollover purpose. By the way, if you're familiar with Ping Castle, this issue is also detected by it. So when you don't regularly rotate the password of a krbtgt account, the Ping Castle will report that as well, and also provide you with some detailed instructions on how this can be achieved. This brings us to the end of the first part of this video series about Kerberos. If you have any questions or remarks, please feel free to leave a comment and we'll gladly follow up on that. Thanks for watching.